Hello and welcome. I need to open our broadcast today by explicitly stating that this is an AI generated analysis, but we are thrilled to welcome you, the listener, to our comprehensive analysis.
Yeah, thank you. And our mission for this detailed technical review is, very clear. We intend to strip away all that constant marketing hype surrounding specific transient software tools.
Right, the shiny new objects.
Exactly. Instead, we will focus entirely on the fundamental, enduring concepts of the data engineering lifecycle. Because if you manage or interact with data systems, you already know the stakes of this profession. We will explore exactly how these underlying mechanisms function, and we are deliberately using clear, accessible language to ensure these complex architectural principles remain, entirely actionable for your own organization.
Okay, let's unpack this. We must start with this sort of digital janitor problem. Imagine paying a team of brilliant, highly specialized data scientists millions of dollars every year, only to realize they spend 80% of their time doing the digital equivalent of janitorial work.
It happens everywhere, unfortunately.
Yeah. Right. For anyone working in the industry, you have likely seen data scientists just paralyzed because they cannot access clean, reliable data. And the book references this vital framework called the Data Science Hierarchy of Needs, which was originally introduced by Monica Rogati.
Yeah, that hierarchy illustrates a fundamental truth. Before an organization can achieve advanced artificial intelligence, or even basic machine learning, it absolutely must build a highly reliable data foundation.
A solid base.
Precisely. Without a dedicated data engineering function, data scientists spend the vast majority of their time just collecting, cleaning, and preparing data instead of actually building predictive models.
Which is what you were paying them to do.
Right. The bottom three foundational levels of that hierarchy are collecting data, moving and storing data, and exploring and transforming data.
So if I can jump in with a comparison here, think of a massive stadium concert.
Yeah.
The data scientists are the rock stars performing on the stage.
Okay, I like that.
Their work is highly visible. They receive all the public applause when their predictive models generate profitable insights. But the data engineers, they're the stage crew and the roadies.
Ah, right.
They build the physical stage, they tune the complex instruments, they run the electrical cables, and ensure the sound system functions perfectly. They manage the underlying physics of the event. Without the roadies performing that heavy lifting in the background, there is absolutely no show for the rock stars to perform.
If we connect this to the bigger picture, by strictly automating those foundational levels, data engineers create a reliable, continuous path to production. They completely remove the burden of infrastructure management from the data science teams.
So they are freeing up the rock stars to just play music.
Exactly.
Yeah.
Therefore, the source material defines data engineering as the development, implementation, and maintenance of systems that take raw data and produce high-quality, consistent information for downstream purposes. It requires a mastery of software engineering, orchestration, and security.
But I must ask a question here, given the current state of technology. Cloud interfaces have become incredibly simple to use, right? Cannot a competent data scientist simply provision their own cloud database and bypass the data engineer entirely?
Well, that is a very common assumption,
What?
but it entirely ignores the complexity of technical scale.
Oh, interesting. How so?
While provisioning a single cloud database is simple, managing the continuous automated flow of terabytes of data across multiple interconnected systems is profoundly difficult. This brings us to the core framework of the text, the data engineering lifecycle.
Right, the 5 stages.
Exactly. It is not about simply turning on a database. It is about structuring a highly reliable daily workflow that can survive unexpected failures. The lifecycle consists of 5 sequential stages: generation, storage, ingestion, transformation, and serving.
And the process logically begins with generation, right? And this first stage, source systems generate the raw data.
Yes, exactly.
A source system might be a global network of smart thermostats, a financial transaction processing system, or a customer-facing web application. And this generated data typically falls into 2 structural categories.
Right, fixed schema and schemaless.
Exactly. It can have a fixed schema, meaning the structure is strictly enforced before the data is written, much like a traditional relational database. Or it can be schemaless, meaning the software application defines the data structure dynamically as it is generated.
And that technical distinction introduces a massive mechanical challenge for the data engineer.
Because of the unpredictability.
Precisely. When an application generates schemaless data, it provides immense flexibility for the software developers. They can add new data fields instantly without asking for permission. However, that exact same flexibility creates absolute chaos downstream.
Oh, I can imagine.
Yeah, if a software team suddenly changes the format of the data they are generating or renames a critical column, the downstream data pipelines designed to process that data will immediately crash.
Wait, so if an upstream application team changes their schema and breaks my processing pipeline, I have absolutely zero technical control over their source system.
Usually, yes, you have no direct control.
That sounds like a complete architectural nightmare. Am I just supposed to hope the software developers do not break my infrastructure? I am curious how a technical professional solves a problem when they do not control the environment where the problem originates.
The authors provide a brilliant approach to this exact scenario. You cannot solve it with code alone. You must use professional diplomacy.
Diplomacy, like talking to people.
Yes, data engineers must establish formal service level agreements, or SLAs, with the upstream application teams. An SLA functions as a data contract.
Ah, I
The
see.
application team formally agrees to notify the data engineering team weeks before making any structural changes to the data they generate.
So you essentially implement a human communication protocol to protect your technical architecture.
Precisely. Furthermore, you enforce this diplomatic contract through automated technical mechanisms, such as a schema registry.
How does a schema registry work in this context?
It acts as an automated Border Patrol checkpoint. If the upstream system attempts to send data that violates the agreed-upon structure, the registry instantly rejects the data or triggers a critical alert.
That is brilliant.
It is. This mechanism prevents the corrupted data from entering the pipeline and causing widespread failure downstream. It perfectly illustrates how data engineering requires a combination of human communication and technical safeguards.
Okay, so once you have safely generated the data and navigated those upstream hazards, you have to actually collect it. This leads us to the ingestion and storage stages of the life cycle.
Right, moving the data into your central system.
The text highlights that ingestion, which is the physical movement of data from the source to your central environment, is frequently the largest bottleneck. You are moving massive volumes of unpredictable data across computer networks.
And to manage this, engineers often use mechanisms like change data capture.
Right, where the system constantly monitors the source database's internal logs and only extracts the data that has changed since the last extraction.
Exactly, rather than copying the entire database every single day, which would be incredibly inefficient.
That makes total sense.
But we must focus closely on the storage stage, because the book presents it as the foundation that physically underpins the entire life cycle. Storage is where we see the most profound architectural shift in modern data systems.
You are talking about the move away from on-premises servers.
Yes, if you have ever tried to scale an older on-premises database during a sudden spike in user traffic, you know exactly how painful tight resource coupling can be. Historically, computing power and storage capacity were permanently locked together in monolithic hardware servers.
Let me offer an analogy to explain the mechanics of that tight coupling. Imagine a large public library. In the old, tightly coupled model, every single book you add to the library must come with a dedicated reading desk physically attached to it.
That sounds incredibly expensive.
It was. If you acquire 1 million new books, you must also purchase 1 million new reading desks, even if nobody is sitting at them. You are forced to buy resources you do not need simply because they are permanently attached to the storage mechanism.
What's fascinating here is that this is a highly accurate representation of traditional on-premises hardware. If you needed more storage capacity for historical data, you had to buy expensive servers that included unnecessary processing power.
And modern cloud environments fix this.
Yes, they completely eliminate this problem by separating compute resources from storage resources. In the cloud, object storage is incredibly cheap and highly scalable. You can store petabytes of data independently.
Wow.
Then when you actually need to analyze that data, you rent computing power temporarily, apply it to the storage layer, and then simply turn it off when your analysis is finished.
So following the library analogy, you build a massive, inexpensive warehouse to store all your books. Then, on any given day, you only rent the exact number of reading desks you need for the patrons who actually show up to read.
Exactly. You are no longer forced to buy them together.
This separation physically prevents resource contention. It also fundamentally changes how we load data, right? Historically, systems use an ETL process: extract, transform, and load.
Right, you had to transform the data before loading it into the database because storage was incredibly expensive.
But now,
Indeed, the separation of compute and storage enables a modern ELT process: extract, load, and transform.
okay, so swap the last two steps.
Exactly. Because cloud storage is so inexpensive, engineers now extract the raw data and load it directly into the cloud data warehouse first. They do not worry about transforming it beforehand.
That saves so much time up front.
It does. Once the raw data is safely stored, they utilize the immense temporary computing power of the cloud to transform it in place.
But wait, if cloud storage is so inexpensive that we just load everything into it immediately, does that not create a massive disorganized mess of raw data?
It certainly can.
Because once the data is successfully ingested and safely stored in that flexible environment, it remains inert. Raw data holds potential, but it provides no immediate business value.
That is a great point.
We must mold this raw material into a usable format, which brings us to the transformation stage.
That is exactly why transformation is so critical. Transformation is the mechanism of applying explicit business logic to the raw data. It imposes order on the chaos.
So you are changing the data from its original unusable form into a highly structured model.
Precise.
We should clarify exactly how that mechanism functions. Transformation takes isolated, messy data points and translates them into a coherent narrative.
Right, like with retail transactions.
Yes, for example, a transformation process takes raw retail transaction logs, normalizes all the foreign currency values into a single standard, filters out internal test purchases, and aggregates the numbers to provide a clear, accurate picture of a company's daily global revenue.
Or, for machine learning applications, transformation extracts specific mathematical features from the text data to train predictive algorithms.
Okay, so after the data is thoroughly transformed and modeled, we reach the final and most critical stage of the life cycle, serving data.
Serving is the ultimate destination where that data is actually consumed by the business.
Right.
The data must be served for operational analytics, business intelligence dashboards, or machine learning applications. However, the authors issue a very strong warning here regarding architectural intentionality.
Here's where it gets really interesting. If you have been in the technology industry for the past decade, you have undoubtedly witnessed the trap of the data vanity project.
Oh yes, the digital hoarding.
Exactly. During the peak of the big data hype cycle, many companies built massive data lakes, hoarding petabytes of data without any clear business use case. They collected everything simply because they had the storage capacity.
Creating massive, expensive repositories of data that were never served or consumed by anyone.
It was essentially a corporate digital hoarding exercise.
To avoid the vanity project trap, a data engineer must work backwards. You must define exactly how the data will be served and consumed before you spend engineering hours building the pipeline to ingest it.
That makes perfect sense.
And because we just discussed the separation of compute and storage, serving data to multiple users is now highly efficient.
How does that separation explicitly benefit the final serving stage?
Well, consider a common scenario where a data scientist is training a highly complex machine learning model that requires massive processing power.
Okay.
Simultaneously, a financial analyst is running complex SQL queries to generate quarterly reports. In a tightly coupled traditional system, these two processes would aggressively fight for the same processing resources.
Causing the database to slow down or crash entirely.
Exactly. Because modern cloud databases separate compute from storage, the data scientist can use one dedicated computing cluster, while the analyst uses a completely separate computing cluster.
Oh, wow.
Both professionals are reading from the exact same central storage repository without causing any resource contention.
They are effectively sitting at different reading desks, looking at copies of the same library book without ever bumping elbows. That is a brilliant mechanical solution.
It really is.
So we have now traced the 5 stages: generation, ingestion, storage, transformation, and serving. But the book emphasizes that a pipeline does not run in a vacuum. What keeps this entire sequence from collapsing under its own weight?
The authors identify continuous practices that wrap around the entire life cycle. They call these the undercurrents.
Cool. What are they?
There are 6 specific undercurrents: security, data management, data ops, data architecture, orchestration, and software engineering.
So these are not separate sequential stages.
No, they are constant responsibilities applied to every single stage of the life cycle simultaneously.
Let us examine orchestration specifically to understand how an undercurrent actually functions in practice. You have all these distinct stages: ingesting data, transforming it, serving it.
Right.
They do not just happen randomly. How does the system know when to execute the next technical step without human intervention?
Orchestration provides the precise timing and the dependency management. An orchestrator is a specialized software tool that manages a directed acyclic graph, commonly known as a DAG.
A DAG.
Yes. The DAG defines the exact logical sequence of operations. For example, the orchestrator constantly monitors the storage layer. The moment the daily ingestion process completes successfully, the orchestrator automatically triggers the transformation job.
And what if something breaks?
If the ingestion fails, the orchestrator instantly pauses the pipeline and sends an alert to the engineering team. This strict dependency management prevents the system from attempting to transform incomplete data, which would corrupt the downstream reporting.
It acts as the central nervous system for the entire data architecture. That is fascinating.
It is. Another fascinating undercurrent is data ops, which applies software engineering discipline to data.
Right, because historically, data professionals just wrote code directly into the production database.
Exactly, which is very risky. Data ops introduces mechanisms like continuous integration and continuous deployment, or CI/CD.
So now, when a data engineer writes a new transformation script, it is automatically tested in an isolated environment before it is ever allowed to touch the production data.
That rigorous testing is essential for stability. Speaking of structural stability, the book pivots significantly to define the rules of good system design.
Chapter 3, right. It outlines several core principles for designing robust architectures.
Yes, the very first principle dictates that engineers must choose common components wisely.
Which raises an important question regarding organizational design. How does a company balance the need for standardization with the requirement for technical flexibility?
It is a delicate balance.
Right, because if every team uses completely different tools, you create impenetrable communication silos. However, the authors strictly warn against forcing a rigid, one-size-fits-all technology stack onto every department.
This raises an important question, right? If you force an advanced machine learning team to use the exact same basic data processing tool as the marketing analytics team, you will severely damage the productivity of those highly specialized engineers.
So what is the solution?
The solution is to mandate common components only for the foundational layers, such as a universal version control platform or a shared central object storage system.
I see.
Above that unified foundation, you allow individual teams the flexibility to choose the specific computing tools they need for their specialized daily tasks.
Another critical architectural shift discussed is Principle 8, which mandates prioritizing security throughout the entire lifecycle. The fundamental mechanism of security has changed entirely.
Oh, drastically.
Historically, corporate networks relied on a hardened perimeter model. It functioned identically to a physical castle surrounded by a moat. If a user or a server was inside the castle walls, they were implicitly trusted.
And the massive vulnerability with that castle and moat model is that if an attacker manages to cross the moat, they have completely unrestricted access to everything inside the network.
Which is terrifying.
It is. Modern architecture requires a zero-trust security model. In a zero-trust framework, no user, no application, and no server is trusted by default, regardless of their location inside or outside the corporate network.
To understand how Zero Trust functions mechanically, you must realize that every single request for data is treated as if it originated from a hostile external network.
Exactly. The system strictly authenticates the identity of the requester and authorizes their specific access level for every single transaction.
Even internal database servers must constantly prove they have permission to communicate with each other.
Yes. Beyond modern security, the architecture must also make logical financial sense. The book introduces a vital concept called total opportunity cost of ownership, or TOCU.
TSUSO.
Right. The authors heavily emphasize that evaluating a new technology requires far more than simply calculating the initial financial cost of purchasing a software license. You must weigh the severe cost of lost opportunities.
Total opportunity cost of ownership measures the hidden costs of inflexibility then.
Precisely. When evaluating a system, a technical architect must ask, how much engineering time will be wasted maintaining this specific tool?
Or how difficult will it be to integrate this software with future technologies?
Yes. If a system requires constant manual intervention, it aggressively consumes the engineering resources that could have been spent building profitable new features for the business.
Consider a commercial real estate analogy to visualize this financial concept clearly. Purchasing traditional on-premises hardware is a massive capital expense. It is exactly like signing a rigid 10-year commercial lease for a sprawling office building.
You are permanently locked into that specific physical space.
Exactly. If your company suddenly shrinks due to market conditions, you are still paying for empty floors.
Hmm.
If your company doubles in size overnight, you have absolutely no room to grow.
Yeah.
You suffer a massive opportunity cost because you lose the mechanical ability to pivot.
Conversely, utilizing cloud infrastructure represents a flexible operational expense.
Right.
The operational expense model is like renting a flexible co-working space on a daily basis. If you need 50 desks today and only 2 desks tomorrow, you adjust your spending instantly.
This cloud approach provides immediate architectural agility.
It does. You never suffer the opportunity cost of being locked into outdated hardware because you can simply stop renting the old tool and immediately start renting a newer, more efficient technology when it hits the market.
So, what does this all mean? When we synthesize the core arguments of this comprehensive analysis, the reality of the profession is clear. Data engineering is no longer defined by babysitting massive, complex hardware clusters.
No, not at all.
It is no longer about fighting against the physical limitations of rigid servers. Modern data engineering is the continuous management of a holistic life cycle.
It is the sophisticated process of guiding data from unpredictable source systems safely through automated ingestion and transformation, all the way to serving it for critical business decisions, while utilizing highly flexible, secure, cloud-based architectures.
As we conclude our analysis today, I want to present a final concept for you to consider based on the current trajectory of these technologies.
Okay.
We are currently witnessing the rapid rise of highly accessible transformation tools such as dbt and the widespread adoption of analytics as code.
That is a huge trend right now.
Yeah. Today, business analysts who write basic SQL are routinely executing the complex data transformations that highly specialized data engineers used to write.
And because the software interfaces have become incredibly intuitive, the daily tasks of the profession are shifting.
Right.
As cloud platforms become increasingly abstracted, automated, and simple to operate, we must ask a critical question regarding the future of the industry.
Which is?
Will the specific job title of data engineer eventually disappear?
Wow, really?
The author suggests the role is evolving so rapidly that it may soon be replaced by the title of data lifecycle manager.
A data lifecycle manager.
Yes, this represents a profound professional evolution. The daily work is transitioning away from writing low-level infrastructure code and moving toward the high-level management of automated, interconnected data systems.
That is a fascinating evolutionary shift to consider and a perfect architectural thought to leave with our audience.
Absolutely.
We strongly recommend that you read the actual book, Fundamentals of Data Engineering by Joe Rees and Matt Housley, to fully grasp the technical depth of these frameworks.
It is an incredible resource.
To all the friends of the show listening today, we encourage you to subscribe to the program so you never miss our upcoming technical analyses. We wish you a great day and thank you for joining us.